Calculus 2 friends. Here we are in section 7.4, and we're going to look at a whole new type of function called the hyperbolic functions. And this is exciting because the last time you learned about a new function was when we talked about with the fundamental theorem of calculus that the integral can actually be a function. And before that, the last new function that you learned about may have been probably the sine and the cosine, the tangent, maybe the exponential and the logarithmic. Those were functions. Remember, a function is just like even x squared plus 5. That's a function. You know, it's some sort of way to describe y in terms of x. You know, that's one way to describe a function. Now, and remember, functions are have some properties that for every x there is one and only one y. Right now, you will learn in Calculus 3 about equations or description models that are not functions, and you can do calculus on them as well. But right now, we're still talking about a whole family of different types of functions to describe the real world. And so this is it's exciting day because you're going to learn about a new type of function called the hyperbolic functions, and that's cool too because that's cool language. You know, hyperbolic sounds kind of out there. So honor me here with a little journey into your textbook where I read to you. So this is the portion of the class where Mrs. Brooks reads to you, but I'm going to do that just to instill that the book is important, and he does a nice job sort of setting the groundwork for these functions. Now, I'm going to spend a lot of time just showing you how to integrate and differentiate and work with the functions once we know what they are. Okay, so if we go to the computer, and this is online, I just went to your textbook, section 7.4, hyperbolic functions. It says the hyperbolic functions are formed by taking combinations of the two exponential functions, e to the x and e to the negative x. The hyperbolic functions simplify many mathematical expressions, and they are important in applications. For instance, they are used in problems such as computing the tension in a cable suspended by its two ends. So you're actually going to learn that that's called a catenary. You know, the cable that is suspended between two telephone poles, the shape that forms is called a catenary, and it can be described by a hyperbolic function, as in electrical transmission line. They also play an important role in finding solutions to differential equations, but in this section we give a brief introduction to hyperbolic functions, their graphs, how their derivatives are calculated, and why they appear as more important antiderivatives. Okay, now you may remember what an even and an odd function is. An even function is like y equals x squared. And what happens with an even function is it has y-axis symmetry, and you can describe it as, for example, if their function is y equals x squared, then if x is 2 or if x is negative 2, you get exactly the same y. You get 4, right? So for every x or negative x, you get the exact same y. That's an even function. Now, an odd function has the property that it has what we call origin symmetry, and it's like x cubed is the most obvious odd function. And it has the property that when you put an x in, if you put the negative x in, you get exactly the opposite. So, for example, for x cubed, if you put 2 in, you get 8. But if you put negative 2 in, you get negative 8. Okay, so those are odd functions and even functions. Well, it turns out that every function that is defined on an interval centered at the origin can be written in a unique way as the sum of one even function and one odd function. And then they do the decomposition, which I'm not going to go into, but that's just interesting, okay? So any function that's defined from negative infinity to positive infinity, it would be centered at the origin, obviously. And so any of those functions then can be written in terms of their even part and their odd part. So if you want to be crazy, you can express e to the x as e to the x plus e to the negative x divided by 2. And e to the x minus e to the negative x divided by 2. That's its even part and its odd part. And let me just come to the laptop and show you that may seem like a really crazy thing to do. But for fun, e to the x can be written as e to the x plus e to the negative x divided by 2 plus e to the x minus e to the negative x divided by 2, where this is what we call its even part, and this is what we call its odd part. Okay, and this plus e to the negative x divided, you should be able to see that if you split this out and put them each over 2, these would cancel, and then you'd have half the e to x plus half the e to the x would actually be e to the x. So it's like if you wanted to be really complicated about e to the x, you could write it this way. And I promise I'm going to go and do some research about like who in the world even thought of this and why, but it turned out to be really handy, so they thought of it, and now I'm telling you about it. Okay, now the even part of e to the x, which is this first part right here, is called the hyperbolic cosine. And the hyperbolics, okay, the even and odd parts, the first one, okay, sorry, I'm talking too much. This function right here we're going to describe as the hyperbolic cosine, which we write as cosine with an h and then an x. And we say cosh, like, it's funny, it rhymes with, what did he say it rhymes with? Sorry, hold on. He gives you a little, rhyming with gosh. Oh, so I have it wrong. It's cosh, and then the hyperbolic sine is a sine with an h, and we say it as cinch, rhyming with pinch, okay? But you often will just hear me say hyperbolic sine because it just feels weird to say cinch. But anyway, and cosh, rhyming with gosh, okay? So this part, which is the even part of the decomposition of e to the x, is the hyperbolic cosine. And this part, which is the odd part of e to the x, is the hyperbolic sine. And you may remember that cosine is an even function and sine is an odd function. So that may have been one of the reasons why they chose to name the odd part sine and the even part cosine. I don't know if you remember that or not. Okay, so let's see if there's anything else in the textbook that I wanted to look at. Let's see. Right, okay, so we have the n. Okay, so it says the even and odd parts of e to the x, called the hyperbolic cosine and the hyperbolic sine of x, respectively, are useful in their own right. They describe the motions of waves in elastic solids and temperatures and the temperature distributions in metal cooling fins. And the center line of the Gateway Arch to the west in St. Louis is a weighted hyperbolic cosine curve. Okay, so there you go. All right, so in your notes, I went ahead and took this from the textbook so that you could have it. I don't know how well it printed. Did it print okay, or did it not look so good? Prints okay? Okay, good. And they just go ahead and give you these functions, these new functions, the hyperbolic sine, and then they give you what the graph looks like, and then the hyperbolic cosine, and then, of course, the hyperbolic tangent is just as you think it's going to be the hyperbolic sine divided by the hyperbolic cosine. So it looks like this. And then the hyperbolic cotangent is just the reciprocal of the hyperbolic tangent. So it's going to have a lot of the same trig properties from before. And it looks like that. And then the hyperbolic secant is just the reciprocal of the hyperbolic cosine. And then your hyperbolic cosecant is the reciprocal of the hyperbolic sine. Okay? So those are your little functions. All right? And then you remember how there were trig identities, like cosine squared plus sine squared equals what? What's sine squared plus cosine squared equal to? Right, that formula is the meaning of life. Well, you might wonder if there is a identity for the hyperbolic cosines for the hyperbolic functions that is similar, and it turns out, yes, the meaning of life for the hyperbolic functions is that the hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. And so if I'm going to call that the meaning of life, I probably need to prove it. And so I will show you just one of these in a proof. And you can do the others for fun if you want. in your book or however you want to do it. But let's just play with that one. And then we'll just do we'll just start kind of doing examples and stuff. So the hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. I'm doing this without a net. I haven't practiced. I'm excited. Okay, what you want to do is start with their definitions, what the definition of the hyperbolic cosine is. Well, we were just told that it was e to the x plus e to the negative x divided by 2. Okay, so we're going to say e to the x plus e to the negative x divided by 2, and then we're going to square that. And then we're going to subtract e to the x minus e to the negative x divided by 2, and we're going to square that. And so hopefully, if we do this work, just checking to make sure I did that right, if we do this work, we're going to get 1 in our computation. Okay, so the first thing I'm going to do is get rid of this fraction because that stresses me out. So since it's squared, that's going to be a 1/4, and I'm going to have e to the x plus e to the negative x. And that's going to be squared, 1/4, which I said but did not write. And then, are you guys cool that the 1/4 would come out of that one as well? And I can write this as e to the x minus e to the negative x, quantity squared. Okay? So hopefully all of this is equal to 4, but let's see. So we have the 1/4, and if we FOILed this out, so this would be e to the x plus e to the negative x times e to the x plus e to the negative x, we would get e to the e to the x times e to the x, which is e to the 2x, right? Because when the bases are the same, you add the exponents. And then this will be e to the negative x e to the x times e to the negative x, which is bases are the same, you add the exponents, so that's going to be e to the 0. E to the negative x times e to the negative x, again, add the exponents, so that's going to be e to the 0. And then e to the negative x times e to the negative x is going to be e to the negative 2x. Right? Okay, minus, I'm going to do the same thing on this one, e to the x minus e to the negative x, and then e to the x minus e to the negative x. All right, e to the x times e to the x is e to the 2x. E to the x times e to the negative x, this is going to be minus e to the 0. This will also be minus e to the 0, and this will be plus e to the negative 2x. So if you're having a good day, you should see, because you're subtracting all of this, this is going to cancel with this, and then this is going to cancel with this, and then e to the 0, of course, is 1. So this is 1, this is 1, this is 1, and this is 1, but you're subtracting the 1s, and so that makes 4. So you are going to get 1/4 of 4, which is in fact equal to 1, and so you have proved that it is true that the hyperbolic cosine of x minus the hyperbolic sine of x is equal to 1. So if you were asked to prove any of these identities, you would start with the definition of what the hyperbolic cosine or hyperbolic sine is. Okay? And if you wanted to get to, remember there were children of the, here's the children of, I call them children of Big Daddy, sine squared x plus cosine squared x. You could get to the, you could derive these. On these, to get the hyperbolic tangent squared x equals 1 minus hyperbolic secant squared x, you would not have to go through the definition to do that. Once you have the definition of hyperbolic tangent, once you have proved this one, once you know that that is true, that the hyperbolic cosine of x minus the hyperbolic sine of x is equal to 1, then if you wanted to get one of the other, like the tangent one, you could just divide everything by either hyperbolic cosine or hyperbolic sine squared. So this would be 1 minus, this is the hyperbolic tangent, and this, of course, is the hyperbolic secant squared. And so then you can clean this up, and you do get that the hyperbolic tangent squared of x is equal, let's see, I have to minus that, but then I have to divide by a negative, so it would be 1 minus the hyperbolic secant. So once you've proved, one of them, you can derive some of the others in a little bit more simply way. Okay, so that's just a little whatever. You've done that sort of stuff before. Okay, so the first homework problem, you get to kind of just play with this new idea. And so if you're told that the hyperbolic sine, or the sinh of x, is equal to -3/4, then they ask you to find the remaining hyperbolic functions. So you should use your Big Daddy identity or theorem, which is that the hyperbolic cosine squared of x minus the hyperbolic sine is equal to is equal to 1. Now, we know that the hyperbolic sine is equal to -3/4. So the hyperbolic cosine of x minus the opposite of 3/4 squared is equal to 1, right? And so then the hyperbolic cosine of x is minus 9/16 is equal to 1. And so the hyperbolic, okay, so should I start saying cosh? Does that work for y'all? It feels so weird for me. Cosh squared of x is equal to, if I move that 9/16 over, that's going to be 25/16. Yes? All right, and then the hyperbolic cosine of x will just be the square root of 25/16, which is equal to 5/4. Now, you may say to me, Miss Brooks, how do you know that it is positive? And I will tell you that when I look up here at the picture of the hyperbolic cosine, I see, do you see from this graph, it's always positive. It's never negative. So I don't have a plus or minus when I was solving that. The hyperbolic cosine is always positive, so I don't have to worry about that. All right, so how then do you think I will get the hyperbolic? Here's an easy one. How about hyperbolic secant? What's hyperbolic secant going to be? It's just the reciprocal of the hyperbolic cosine. So it's 1 over 5/4, which, yes, is 4/5. And then what about the hyperbolic cosecant? Well, the hyperbolic cosecant is 1 over the hyperbolic sine, or sinh, which is going to just be the reciprocal there, which is -4/3. And then your tangent, your hyperbolic tangent, is, of course, just your hyperbolic sine divided by your hyperbolic cosine. So that's going to be the -3/4 divided by the 5/4, which is -3/5. And then your hyperbolic tangent, cotangent, sorry, is equal to the reciprocal of the tangent, which is equal to -5/3. Fun, easy, cool, right? Oh, don't worry, that won't last. All right. Rewrite the expression 2 hyperbolic cosine ln x in terms of exponentials and simplify the result as much as possible. So just, remember that the hyperbolic sine and cosine were defined as the breakup of the exponential into its even and odd parts, right? So you can take this 2 hyperbolic cosine ln x, And you can write that as 2. Now, hyperbolic cosine is, by definition, e to the x plus e to the negative x divided by 2, right? So in this case, it's going to be e to the ln x plus e to the negative ln x divided by 2, right? Okay, and so then the 2's cancel here, and you get e to the ln x plus, you know, you want to like unpower rule this, so bring that negative up to the top. So this is e to the ln x to the negative 1. Is that familiar? Yes? Okay, and so then this e to the ln x is just x plus e to the ln x to negative 1 is just going to be x to negative 1. So you get x plus 1 over x, which you can leave like that, or you could get a common denominator if you wanted, x squared plus 1 over x, if you multiply that one by x over x. Fun? Whatever. Okay, so there's your first 2. I haven't done any calculus yet. Y'all ready for some calculus? All right, without loss of anything, or actually without proof, but you can read it in your book if you want. All your familiar derivatives are going to work out. And I mean, like, you can do this. How would you prove this? I'm not going to, okay? But if I were to prove the derivative of a hyperbolic sine is a hyperbolic cosine, I would go ahead and describe the hyperbolic sine as e to the x minus e to the negative x over 2, and take the derivative of that, and then I would note that it was e to the x plus e to the negative x divided by 2. Probably in your head you can see it, you can feel it, because the derivative of e to the x is just e to the x. Well, derivative of e to the negative x is going to be negative e to the negative x, and if you had a minus, that becomes a plus, which now makes it the cosine. So there, I proved it. Okay? So all of these friends still are friends with you. Notice that the derivative of the hyperbolic cosine is positive, which is a little bit different. You know what I'm saying? And you've got your hyperbolic tangent. Notice it's positive. Or was it positive for the tangent? I've forgotten. But whatever. You do have some negatives in here, but these should be somewhat familiar. And then, of course, you have all your integrals that are here. Okay. Now, let me show you and remind you that at the very beginning of this, what is this? At the very beginning of this class, I suggested that you always, you know, implant into your brain this formula sheet that I stole from another book. I didn't steal it. You're allowed to steal 1 or 2 things with permission. I mean, you know, it's not, whatever. It's something about, as long as you're passing on and making people smart, it's not really taking copyright or something. You know, it's good that I'm putting this all in the recording. I can take one thing, and I did take this one thing from this other book because it's really, really good. And notice, here you go. Here's your derivatives. And the reason I like this sheet better is because it reminds you of the chain rule. Like, if it were the hyperbolic cotangent of x squared, then you would do negative hyperbolic cosecant x squared times 2x. You know, it's reminding you of the chain rule there. That's why I like that this derivative sheet better than the one that he has available for you, because it's reminding you of that chain rule. But so what happens today is you're going to learn 19 through 36, because we're going to do all the hyperbolics and then their inverse functions as well, and you'll see all of their derivatives there. Okay, so they're already on your sheet, and then they also exist. I think there's some. Oh, I guess not. There aren't any. They didn't show up on the basic integration formulas on this sheet, but you can kind of see that if you were to integrate this, well, you better get back to that, right? So, I mean, you kind of still have, if you have a derivative, you have an integral. Right. It may not be the one you want, but you still have one. Okay. All right, so let's go back to this section. Okay, so this sheet is here for you, or these formulas are here for you to help you work these problems, like these examples 3 through 5. Now we're gonna do. Okay, but I mean, gosh, we're good at this stuff, right? Because all this is what? Stuff you already know. You already know how to use the chain rule, or in this case, the product rule and the chain rule. So you're going to knock this baby out. So like this is your U and this is your V, right? And remember the product rule is U times V prime plus V times U prime or something like that. So if U is equal to 2t to the 1/2, then U prime is equal to t to the 1/2 minus 1, which is negative 1/2, or 1 over the square root of t. If V is equal to the hyperbolic tangent of the square root of t, then V prime is going to be equal to the derivative of the hyperbolic tangent, which is secant squared, hyperbolic secant squared of that, times the derivative of that, which is the derivative of the square root of t is 1 over, 1 over 2 square roots of t. Do you all agree with that? Because the 1/2 comes in front and then, okay. All right, so it didn't have it here because there was a 2 there. All right, and so then U times V prime is going to be, this will be my derivative now, Y prime is going to be U, which was 2 square roots of t, times U prime, which is 1 over the square root of t. Just kidding. U times V prime, which is hyperbolic secant of the square root of t times 1 over 2 square roots of t, plus
the conference is scheduled to end in 2 minutes.
E, which is the hyperbolic tangent of the square root of t times U prime, which was 1 over the square root of t. And so then, on this one, these cancel. So you get Y prime equals the hyperbolic secant squared of the square root of t plus the hyperbolic tangent of the square root of t over the square root of t. And I'm happy with it left like that. I don't know if the computer wants a common denominator, then you would just multiply this by the square root of t. It probably is happy with that. Fun? Okay, good. All right, I'm guessing that I have a typo here, and I want that to be, yes, I have a serious typo. This should have been a 1. I'm sorry. It's a serious typo. That's a 1. Did you leave me, Brandon?
No, I'm still here.
Okay, I just lost your image. Okay, but you're back now. So I want this to be a 1. 1 minus ln secant A. Okay, so we could use, we could just, you know, I think it's probably a good idea to use the product rule. I don't think I would multiply this out, because if you multiply it out, then you're still going to have to use the product rule on that secant A, ln secant A. So let's just
Your conference is now over. Goodbye.
Like that woman. Treat this as a U, and I'm going to treat this as a V. Okay, and so U equals the hyperbolic secant of A. So U prime, what's the derivative of the hyperbolic secant? I don't know. Let's see. It is negative hyperbolic secant, hyperbolic tangent. So I guess I lied. This little chart that he has does have the U stuff in there. So he does have the chain rule implied, which is nice. Okay, so it's the negative hyperbolic secant of A times hyperbolic tangent of A. Okay? And if V is equal to 1 minus the ln of the hyperbolic secant of A, then V prime is equal to, all right, the derivative of the ln is 1 over the hyperbolic secant of A, 1 over x, right? But, and I'm not going to put that negative, because when I use the chain rule and take the derivative of this, the negative is going to cancel, and so I'm going to get the hyperbolic secant of A times the hyperbolic tangent of A, right? Well, this is going to be fun, right? Because these cancel, and so I get just the hyperbolic tangent of A. What do you think about that? Yeah, it's rocking. Okay. So now I've got to do my derivative. Remember, my derivative is u times v prime plus v times u prime. So that's going to be u, which is the hyperbolic secant of a, times that, which is the hyperbolic tangent. I'm so tired of saying hyperbolic, like my lips hurt. Hyperbolic. All right, and then the v is, what was v? I'm all running out of room. All right, let me try to see him. La la la. Okay. U is the hyperbolic secant. V prime. What was V prime? Hyperbolic tangent. Plus V, which is this big old long thing, times U prime, which was this thing. Okay. And it's kind of fun, I guess. Hyperbolic secant is 1 over I don't know. I wonder how much they want us to simplify this. Quite a bit. So okay. Do you guys agree with it? Because I'm looking at the solution. It looks a little bit that, and then it's that over that. 1 over the secant of a. The tangent. And so this is u times v prime plus v times u prime. All right. So I'm sorry, hold on just a second. I'm looking at what they did. I have no idea what they're doing. They're being really weird. Okay, so this is where this online homework could get ornery because of how they simplify it. But I really don't think there's much that you can do here.
Miss Brooks?
Yeah?
Your U prime, you didn't write it down right.
Say it again?
Your U prime is supposed to be negative secant A.
Thank you, thank you, thank you, thank you. Oh, thank you. All right, so this is U times V prime plus V times U prime. And U prime is the negative secant A tangent A. Times the tangent. My excuse is, since I've started teaching, I've gone to this method where I find them all differently, but I don't use. If I were just doing this by hand, I would just do it without doing that, and that's my excuse. I actually confused myself. I guess I'm not concentrating. Okay, so this is hyperbolic secant A tangent A. All right. Well, I guess what I want to do is notice that I can factor that out. It's common to both of them. To this term, hyperbolic secant A, and then it's here too. So I'm going to factor it out, and what I have is 1 plus this thing, which is 1 minus, well, because of this negative, it's actually going to be negative. So this is going to be negative 1 plus the ln of the hyperbolic secant of A. All right, and then the 1 plus the negative 1, these are going to cancel out. And so I just get the hyperbolic secant of A times the hyperbolic tangent of A times ln hyperbolic secant of A. Whew, thank you, Brandon. I got stuck there, didn't I? All right, I promise to do better on this one. I hope. Okay. I'm going to do it without all that UV prime stuff and just kind of show you how I do it if I were just doing this for homework. All right, so I would do, see, in my brain, I do first and second. I do the derivative of the first times the second plus the derivative of the second times the first. But this is just how I do it. All right, so the derivative of the first is 2x times the second, which is the hyperbolic secant of the ln of x, plus the derivative of the second. The derivative of the hyperbolic secant is negative secant tangent. So this will be negative hyperbolic secant ln x, hyperbolic tangent ln x, times the derivative of ln x, which is 1 over x, times the first, which is x squared plus 1. Okay, so I did the derivative of the first times the second plus the derivative of the second, which was quite long, times the first. Is that okay too? All right, now, what do I notice? I notice that the hyperbolic secant ln x is common to both terms. So I could write this as hyperbolic secant ln x, and then I'll have a 2x, and then I'll have a minus, and then I'll have tangent ln x times x squared plus 1 all over x. And, you know, I don't know. Let's see if they want to clean that anymore. Oh, yeah. They want to clean that a ton. Okay. All right. So, and I forgot to put my hyperbolic. All right. Didn't I say that I was going to be fun for me, and so that I totally jinxed myself? I think that I wish that I had done this problem slightly differently. What I wish that I had done is reminded myself that whenever I see an ln x within the hyperbolic secant, maybe it would be a good idea to simplify it first with the definition of the hyperbolic secant. Because remember, it has that e to the x, and the e to the ln x stuff in it would be a good idea. So this is what you get when you have, well, nothing. A cheap teacher, I guess. A teacher that, I don't know. I'm sad. Okay. What you should have done probably, this what I did is not wrong, but a better approach is to simplify first. Okay, and so if I come up here and I look at what is the definition of the hyperbolic secant, I see that it is 2 over x, 2 over e to the x plus e to the negative x. So I will say, where was I? Recall that the hyperbolic secant of x is equal to 2 over e to the x plus e to the negative x, because it's just the flip of the hyperbolic cosine. All right, so the hyperbolic secant of ln x will just be 2 over e to the ln x plus e to the negative ln x, right? Well, e to the x is just, e to the ln x is just x, and we already discussed this. E to the negative ln x is just going to be x to the negative 1, right? And then this will clean up as 2 over x plus 1 over x, and then you'll get a common denominator here, and then flip it, which is going to be 2x over x squared plus 1. Did I lose anybody there? Did I lose you, Brandon? Common denominator and the flip. Can you do it in one step? because I multiplied this by x over x. So that made x squared plus 1 all over x, and then I flipped it. Yeah? Yeah, he's got it. Okay, so, Okay, so so now I can take this bad boy and stick it right in here for all this stuff, which is going to make this problem, so much easier. Because now I see that y, which is will be x squared plus 1 times 2x over x squared plus 1. And those bad boys cancel, and so then y prime is 2. Okay, sorry, should have cleaned it first. Lesson learned. Clean your house first before you try to look for whatever's lost. All right. Maybe it will come to you. It will appear in the cleanness. All right. Well, we've got the hyperbolic sign, and it turns out that we always love to undo what we done did. So we need an inverse function for the hyperbolic sign. So we have the sinh and the inverse sinh, okay? And the hyperbolic sign is this yellow one right here. And you might remember that inverse functions reflect across the line y equals x. So there's just no problem with the inverse sign, no domain problems or anything like that. Now, the hyperbolic cosine, remember, was sort of a parabola, or parabolic, not really. It was a UE sort of shape. And that's not one-to-one. So you're not going to have a inverse cosh unless you restrict the domain. So as long as you only consider positive x's, then you can have a nice inverse function here, which is the hyperbolic inverse function right there. All right, so those are your graphs, and then these are your graphs of your other inverse functions here. Okay? So everybody happy with that? So guess what? They have some identities for inverse hyperbolic functions, which we're not going to derive. These are kind of interesting. The inverse sinh of x is equal to the inverse cosine of 1 over x. The inverse cosecant of x is equal to the inverse sine of 1 over x, and the inverse cotangent of x is equal to the inverse tangent of 1 over x. All right. The derivatives of these functions are fun because they just look so crazy, but you know, you can read in your book if you want to derive them, or we can just take them as they are. The inverse hyperbolic sine derivative is 1 over the square root of 1 plus u squared times du dx. And then we have all of these derivatives here, and we do have some restrictions on them. And then I think we have some integrals too. Did I put them? Well, we'll get them in a minute. Okay. All right, so now let's do some more derivatives, and let's see if I can do a better job with these. We didn't do any integrals, did we? Are y'all sad? Because we haven't done any integrals in a while. I know we'll do some. Don't worry, I think there's integrals coming up. I guess I'm just sort of moving along here. Okay, so get here. This problem, what you're going to want to do is just go ahead and take your derivative. This one's not going to be so bad. Just using the formula. The inverse, oops, I bet, no, I didn't. I'm mixing up, this is just to mess with your brain. I'm mixing up the cosine, the regular cosine, and the hyperbolic secant, okay? So you have to remember the derivative of the regular cosine, which I don't. I mean, the regular inverse cosine. So that's when you can go back to your sheet, and you can come over here, and you can look for the regular derivative. And on this one, remember that arc cosine is the same as cosine to the negative 1. Right? Okay. So the arc cosine, the derivative of the arc cosine is this negative u prime over square root of 1 minus u squared. So you will come back here and you will write the derivative of the inverse cosine as negative, it was u prime, which in this case is u is just x, so negative 1 over the square root of 1 minus x squared. And then minus, we're going to have a product rule. This is the first times the derivative of the second, and we just learned the derivative of the arc secant is this du dx over negative du dx over u square root 1 minus u squared. Well, your u here is just x, so the derivative is just going to be 1 over, and then this will be x on the square root of 1 minus x squared. So that's the first times the derivative of the second plus the second, which is inverse hyperbolic secant times the first, which is x. So this is going to just be this. Which is 1. The first times the derivative of this one, the second times the derivative of the first, which is just 1. Okay, and so then that is what you get there. And let's see, you can clean it up a little bit because of this x and this x canceling. And then because it's I lost my negative right here, but this is actually going to be positive when you distribute through, and then you'll have a negative there. So you're going to have negative 1 over the square root of 1 minus x squared plus 1 over the square root of 1 minus x squared minus the hyperbolic secant, inverse hyperbolic secant. And so then that will just clean up to be negative hyperbolic secant, inverse hyperbolic secant. That's a lot to say. Inverse hyperbolic secant of x. Okay. Number. I know it's like inverse. I don't know what it is. I hate how all my numbers change. Like this was 6. This is supposed to be 7. And this is 8. Bill Gates is messing with my mind here. All right. So here we go. And then that one didn't move. Boy. All right. So here's your next example. I know, time to stretch. It's a 7th inning stretch. We have a bunch more of these. All right, so y prime is going to be equal to the derivative of ln x, which is 1 over x, plus the first, which is the square root of 1 minus x squared, times the derivative of the hyperbolic secant, which we just learned, the derivative of the inverse hyperbolic secant, which is negative x over, or negative 1, because the derivative of that. So it's negative 1 over u over square root 1 minus u squared. So that's going to be x over the square root of 1 minus x squared, plus the derivative of the first, which is, this is 1 minus x squared to the 1/2 power. So its derivative is 1/2 times 1 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. So those cancel. So it's going to be negative x over the square root of 1 minus x squared times the hyperbolic secant, hyperbolic inverse secant. Right? Okay. And so then this is, this one kind of cleans up a little bit because you got the square root here and then down there, so we can cancel those. And so we can write this as 1 over x minus 1 over x plus, or minus, x over the square root of 1 minus x squared times the inverse hyperbolic secant of x. And those cancel, and so then that's what you get, the negative x times the inverse hyperbolic secant of x over the square root of 1 minus x. That's your answer. These are going to be fun to type in on the computer. I should do this homework for punishment. All right. Okay, here's number 8. The inverse hyperbolic sine of x, no, the inverse hyperbolic sine of the tangent of x. All right. The derivative of the inverse hyperbolic sine is 1 over 1 plus u squared du dx. Okay, so this is going to be 1 over, was there a square root in there? I've forgotten already. 1 over square root 1 plus tangent squared x times the derivative of the tangent, which is what? Secant squared. And then I think we can, hopefully they'll just, no. Who remembers what 1 plus tangent squared x is? Yeah. That's that Pythagorean identity. That's 1 over the square root of secant squared x times secant squared x. Now, when you take the square root of this, it has to be the absolute value of 1 over the secant of x, an absolute value, times secant squared x, which is, you see, the thing is, this has to be positive. This derivative has to be positive, and secant is positive and negative. So when you cancel here, you just have to ensure that in the end it's still positive, absolute value of the positive. I mean, you have to make sure it's positive, so you have to put those absolute values in there. Because you can't take the square root. I mean, this is assuming when you take that square root, it's assuming that the hyperbolic secant is positive. Okay? So that's why we put those absolute value there. All right, that was fun. Let's try. Oh, here we've got integrals leading to inverse hyperbolic functions. All right, so if you've got an integral that looks like this, then that's the inverse hyperbolic sine. If you got one that looks like this, that's your inverse hyperbolic cosine. Here's, depending on what u is, here's your inverse hyperbolic tangent. And then here's depending on, or no, this is your inverse hyperbolic secant and your inverse hyperbolic cosecant. Okay, so now we get to do, yay, some integrals, because I know that it's been a little while since we've done an integral, so it's exciting that we're going to do one. All right. So this is number 9. The inverse hyperbolic secant squared of x minus 1/2. Okay, so you have to kind of look and see if you have an integral that will help you with that. And if you come up here to these ones, you will see that the integral of the hyperbolic secant squared is the hyperbolic tangent. So we will come down here and we will say, all right, I'm going to use, this is going to be the hyperbolic tangent. Now, my u substitution, I don't really have to do much because u is equal to x minus 1/2 and du is just dx. So this is just simply the inverse hyperbolic, just the regular hyperbolic tangent of x minus 1/2 plus c. Okay. Does that make sense? That one was easy. I keep saying, I think my brain is getting, I'm saying inverse. This one didn't have any inverse in it though. It's just regular hyperbolics. All right, let's try number 10. Again, no inverses in it. It's got this sectan thing going on, which I feel like there is one that has a sectan, right? You can come up to your little sheet and look for your inverse. of your sectans, for your integral of your sectan, and you do get negative hyperbolic secant, okay, for sectan. So I'm going to use that. But I'll have to do a little u substitution first. If I let u equal the square root of t, which of course is t to the 1/2 power, then du is equal to 1/2 t to the negative 1/2 dt, which is 1/2 square roots of t dt, which is almost what I want. If I put a 2, if I multiply both sides by 2, 2 du then is equal to 1/the square root of t dt. So that's what I get right there, which is that. And so I'll just put a 2 du, so I'll put that 2 in front. So this is going to be 2 times the integral of the secant, hyperbolic secant of u plus the hyperbolic tangent of u du, not plus, just times. And then we learned that this is just what? Negative hyperbolic secant of u plus c. Fun? Yes. Let's do another one, Ms. Brooks, because I just don't get enough of this stuff. No problem. Let's do number 11. All right. On number 11, I'm not going to fall prey to the mistake I made earlier, which is, what? What was that mistake I made earlier? Yeah, if you can simplify, if you've got ln's and e to the thetas and stuff in there, you might want to clean that bad boy up before you try to do anything with it. So the hyperbolic cosine, remember, is the even part of the e to the x. So it was e to the x plus e to the negative x over 2. So let's rewrite this as e to the theta plus e to the negative theta over 2, because that is what it is. All right? So now I can write this as the integral from negative ln 4 to negative ln 2. Notice my 2's are going to cancel there, and I'm going to have e to the theta times e to the theta plus e to the negative theta d theta. Everybody okay? All right, and then I can clean this up. E to the theta times e to the theta is e to the 2 theta. E to the theta times e to the negative theta is e to the 0 d theta. Well, e to the 0, of course, is just 1. All right, so the integral of e to the 2 theta, no, I'm ready to go ahead and integrate, is what? Careful. Scott says his stuff really quietly because he doesn't want, I like to just yell my mistakes out, but he said 2e to the 2 theta, and I said careful, and he's turning red now. Should we look at it? No, just kidding. No, and that's because 2e to the 2 theta is the derivative. It's a common mistake, but the antiderivative, you got to put it over the 2. So sorry to be so mean to you. E to the 2 theta over 2. Plus, all right, Brandon, what's the derivative of 1?
Theta.
What did you say? Theta. It's just theta, yeah. All right. And then this is negative ln 4 to negative ln 2. You could probably ask anybody, did I say what's the derivative of 1? Yeah. So you should have said 0. You were wrong. But you knew that I meant what is the integral of 1, which is theta. All right. But, you could ask anybody at your school, what's the integral of 1, except your math teachers, and they might be like, I don't know. So, all right. Now I got to plug all this stuff in here. All right. So, again, when I see ln 4, I often like to think, well, I'll worry about it in a minute, but ln 4 is also 2 ln 2. because it's 2 squared, and then you can bring the 2 in front. You know, just kind of thinking about that sort of stuff might be a good idea. All right, so now we're going to shove in this stuff in here. So we're going to have e to the 2 times negative ln 2 over 2 minus ln 2. That's your f of b, minus f of a, which is e to the 2 negative ln 4 over 2 minus ln 4. All right. Let's see what we got going on here. Okay. Remember, you can pull this up. Is that right? No. What can I do with this? I can separate these. I don't think I can. God. I'm going to write this as I think I can write that as e to the that's because that's negative 2 ln 2. So I think I can write that as ln 2 to the negative 2. Feeling a little nervous about that. Over 2 minus ln 2 minus, all right, this is going to be e to the, based on the same logic, ln 4 to the negative 2 over 2 minus ln 4. Okay, e to the ln 2, it should just be 2 to the negative 2 over 2 minus ln 2 minus 4 to the negative 2 over 2 minus ln 4. And then this is going to be, this is 1/4 over 2, which is 1/8, minus ln 2. This is 1/16, so this is 1/32, right? Minus ln 4. So this is 4/32, right? So that would be 3/32, 3 over 32 minus, all right, let's be really snazzy. This will be ln 2 plus ln 4, which is 3 over 32 minus the sum of the individual logs is the log of the product, which is ln of 8, which is 3 ln 2, because that's 2 cubed. So this is 3 over 32 minus 3 ln 2. Do I dare look? Oh, no. I missed it by one part. They got just ln 2. Oh. Did I distribute a negative wrong? Yeah, right here. This should have been a positive. Boom, here. Y'all weren't watching, right? It's your fault. Is that right? All right, so I've got a negative here and then a negative here, which made that a positive. All right, so this is 1/8 minus ln 2 minus 1 over 30 plus ln 4. All right, so this is 3 over 32. If I factor this minus out, that's going to make this a minus. All right, let me just clean up right here. Okay, 3 over 32. And then this is minus ln 2, and this is plus ln 4. So I'm going to write this as plus ln 4 minus ln 2. Everybody okay with that? Just switched them around? Okay, and then when you have the difference of the individual logs, that's the quotient of a single log. So this is plus ln 4 divided by 2, which is plus ln 2. Sorry, I goofed that up. Did you get lost in any part of it? Are you okay? All that ln stuff is kind of, I mean, you know, it's just being snazzy. All right, let's try number 12. Okay, it says the inverse hyperbolic cosine of the ln of t divided by t. Now, this one, I actually am not going to, I'm thinking, but I don't know, I'm sure that I'm doing the greatest job today, but I'm thinking that I'm not going to rewrite this one. And the reason why is because if I do a u sub and I let u equal ln 2, then ln t, then du is 1 over t, which is exactly what I have there, right? So I don't think it's important. I don't think on this particular one I should do the cleaning the way I did before. So I'm going to write this as u equals ln t, and then du is 1 over t dt. And so that's exactly what I wanted right there, because there's 1 over t dt. All right? So I'm going to change my limits. I'm going to go from the ln of 1 to the ln of 2, and then I have the hyperbolic cosine of u du. All right? And the antiderivative of the hyperbolic cosine is what? It should feel good. It's just the hyperbolic sign. It's not negative or anything. So this is the hyperbolic sine of u evaluated from the ln of 1 to the ln of 2. Now it would be smart to rewrite the hyperbolic sign as its exponential form, which is the e to the u minus e to the negative u over 2. So this is e to the u minus e to the negative u divided by 2 from ln 1. Well, what's the ln of 1? Okay, so from 0 to ln 2. Isn't it awesome how good you're getting at this stuff now? All right, and so this is going to be e to the ln 2 minus e to the negative ln 2. I'm going to put this 1/2 in the very front. That's my f of b, minus f of a, which is going to be e to the 0 minus e to the negative 0, which is just going to be 0. All right, so this is going to be 1/2. E to the ln 2 is just 2 minus, this negative can come up front, so it's 2 to the negative 1, which is 1/2. All right, and so then this is 1/2 times 2 minus 1/2, which is 3/2. So this is 3/4. Yeah, I got it right without messing up. I rock. Okay, now it says, many calculators have an inverse hyperbolic function, but if not, you can find the solution using the logarithms as defined below. So I should have probably looked to see if your calculator has an inverse hyperbolic function, and so that's what we're going to do right now. I think it does. I don't know. Well, I think it might. I know everything that you want always lives under catalog. So if you go to second and then the 0 button, that's the catalog. And then if you want to find, notice it's in the A, it's in alphabetical. So if you were to hit the C, which is the program button, it'll take you to the C's. Does that make sense? And then you can scroll down and see if you can find the hyperbolic cosine function. It takes a little while. There it is. Okay, so that's one way to get it. Now, it may in fact live like, it could live in the math. Let me hit the math and see if it lives in the math. I want to get out of this, so I'm going to do second quit, and then I'm going to hit math. No, it's in complex. I don't know. It probably lives under one of these, but I don't know. I don't know whether it does or not. It may just, it's easiest just to find under catalog, I think. Is that okay? So if you want, you can do it. So that means that we could have worked that problem with our calculator. We could have done math, and then choice 9 for f int, and then catalog, and then went to the C's, and then scrolled down. Almost like, seems like you might go to the D's and scroll up, but anyway. And then you put that in there, and then it was just of x. Close your parenthesis, and then it was ln1 to ln2. Was that the original problem, or was it? Oh, I'm not even doing the original, but whatever. ln1 to ln2. So ln1, of course, is 0. So from 0 to the ln of 2 with respect to x, yeah. Thank you. Comma 0 to ln2. I'm going to give it to you. That was easier than doing it. Okay. So there you go. That's kind of fun. And you actually could have typed it in from this step if you wanted, from the very beginning, if you had wanted to. Okay, but you wouldn't have gotten to think as hard as you did this way. All right, now it turns out if they don't have inverse hyperbolic functions, then you can use the logarithm ways as described below. And then on these next couple examples, I just want you to, or at least on this number 13, I want you to use the formula above to express the inverse hyperbolic sign of negative 5/12 in terms of the natural logarithms. Well, that should be pretty straightforward. You're going to look at that formula, and you'll see that the inverse sign of x is equal to the ln of x plus the square root of x squared plus 1. So it's the ln of negative 5/12 plus the square root of negative 5/12 squared plus 1, which is equal to the ln of negative 5/12 plus the square root. This is 25 over 144 plus, this would be 144 over 144. So this is the ln of negative 5/12 plus the square root of 169 over 144, which is equal to the ln of negative 5/12 plus 13/12, which is equal to, is that 8? What's 13 minus 5? 8, 9, 10, 11, 12, 13, yeah. God. So this is ln of 8/12, which is equal, 8/12 reduces to the ln of 2/3. So there you go, which you could write as the ln of 2 minus the ln of 3 if you wanted, but you could just write it like that if you want to. Wasn't that fun? That's rocking awesome, Miss Brooks. So you can write the inverse hyperbolic sign of negative 5/12. Let's see if we can find that on our calculator. Does our calculator have inverse hyperbolics? Let's see. Second catalog. Now I want to get to the sign, the inverse hyperbolic, so I'm going to hit S. And when I come down here, there's a lot going on in my calculator. All right, I got an inverse hyperbolic science right there, so I'm going to hit enter. Come on, baby. And then I'm going to do what? Negative 5/12. Negative 5 divided by 12. Close your parentheses, hit enter. All right, and then the ln of 8/12, or 2/3, whatever. Oh. I know. It's like, you even know what your calculator is doing. What is the ln of 2/3? E to what power is 2/3? How does your calculator know that? Second e to the answer is, now my calculator's not going to hit 2/3, but what is that? Isn't that the devil's number? 0.666? Evil. You know, e to what power is 2/3? That's what ln means. I know. But, I mean, if we get to sequence the series at the end of this course, you're going to at least have a basic understanding of the amount of totally rockin' amazing stuff your calculator is doing. And it's because lots of people have been thinking really hard about this stuff for you. So, I mean, dude. Do you ever go like, well, what am I going to do with my life? Somebody already figured out how to do ln 2/3 on the calculator. All right, now number 14 says, evaluate the integrals as the inverse hyperbolic function and natural logarithms. Oh, we get to do both. Fun. Okay, so let's see how we're going to begin on this one. This is 71. We only have, this is our last two. All right, I'm going to let u equal, but you gotta have some thinking first. Inverse hyperbolic functions means, let me see if I can find one of those hyperbolic functions that looks sort of like that one, the inverse integral thing. If I come up here, do you see this inverse hyperbolic secant looks kind of like that one? So it's du over u square root a squared minus u squared. I think that looks about right. See, there's your u and the square root. So this could be my a could be 1, and this is my u squared, right? So if I let u squared equal 16x squared, then obviously u is just equal to, careful, u squared is equal to 16x squared. Then u is just equal to 4x, right? Okay. And then du is equal to 4 dx. Okay, and so if I come in here, I mean, if I look at this thing, excuse me, it's going to be du, and then you've got negative 1 over a. Well, a was just 1. Inverse hyperbolic secant u over a, which will be the 4x over 1 plus c. So we will have negative inverse hyperbolic secant of u over a, which was the 4x. I already forgotten. I I got to write that down. Was it 1 over A? I can't remember these between doing them, and it was negative 1 over A inverse hyperbolic secant U over A. Okay. So it's negative okay, so, and our A is just 1. And so it's 1 over A. So it's just going to be negative inverse hyperbolic secant U over A, which is 4x. And then we can change our limit, or we should probably change our limits. If U is equal to 4x, then this is going to be from 4/5 to 12/13. And that's going to be the inverse hyperbolic secant of 48/13 minus the inverse hyperbolic secant of, this is U. So I should have put a U. This is just U. See, because when I change my limits right there, then this is going to be 12/13 to the inverse, and then this will be plus the inverse hyperbolic secant of 4/5. Okay? And then they also want us to do this, cleaning it up in terms of logarithms. So you can leave it like that, or come in here. I think I might leave this part for y'all, but you're going to do it just like kind of like you did this with your natural logarithm stuff. So see, the inverse hyperbolic secant of x is ln 1 plus square root of 1 minus x squared over x. Do y'all want me to do this? Getting tired. The ln of 1 plus the square root of 1 minus x squared over x. So what you're going to have to do is you're going to have to plug that in. You're going to have to plug in your x to get your each piece there. So inverse hyperbolic secant of 12/13. And then you're going to have a negative in a minute. It's going to be ln of 1 plus the square root of 1 minus 12/13 squared over 12/13. And you have to clean that up. Which is equal to the ln of 1 plus the square root. All right, this is 169. So this is going to be 169 minus 144, which is 25 over 169. And then over 12/13. And then 25 over 169 is 5/13, right? So we can just write this as 5/13. And then you can get a common denominator here. So that's 13/13 plus 5/13, which is 18/13. So this is the ln of 18/13 over 12/13. And then you can flip that and you get the ln of 18 over 12, which is the ln of 3/2. Okay, and then you could go through and do the same thing for the inverse hyperbolic secant of 4/5, and then, you know, subtract, do that minus that, or anyway, this one's going to be negative, and just keep working that, continue this process to determine that it is, it turns out to be the ln of 2, if you did the inverse secant of 4/5, minus the ln of 3/2, which when you have the difference, you can write that as the quotient. So this is the ln of 2 divided by 3/2, which is the ln of 4/3. So all that work to get you to the ln of 4/3. Or you could just type it in your calculator and be done with it. All right. This one, number 15, is kind of fun. And this is the last one, which is why it's fun. And does anybody have an idea on the U sub that we should do there? Oh, this lesson's long today. How about U equals the sine of x? Then du is going to equal what? What's the derivative of the sine? Cosine x dx. So then you're going to have the integral from 0 to pi of 1 over, or du over the square root of 1 plus u squared, right? Which is, if you look at your thing, a number 1, that's the inverse hyperbolic sine. And so this is going to be equal to, you might want to change your limits. The sine of 0 is 0. The sine of pi, maybe we better not change our limits. All right. So what did we decide this was? This was the inverse hyperbolic sine. Yeah, this is so weird. This problem is so dumb. Because when you change your limits, you just get the integral from 0 to 0. So you don't even have to do anything because the answer is 0. I mean, you could work it all out. It's kind of dumb. So, I don't know. I mean, you could say it's the inverse hyperbolic sine of 0 minus 0, inverse hyperbolic sine of 0, but that is still 0. So, okay. That is it for this section. Wow.